gradient in concentration in a situation where we're looking at distance scales which are long compared to the mean free path of a particle moving in some material or fluid or substrate, that the motion is diffusive. The particle makes a kind of random walk. Its direction of motion gets renewed on some characteristic time scale during which it travels a characteristic length scale. That's the mean free path. And then there will be a flux, according to the diffusion law, proportional to the gradient of the concentration of particles. Flux. The concentration tends to flow from regions of high concentration to regions of low concentration for purely statistical reasons. And the constant appearing in the equation is called the diffusion constant, or diffusivity. Using the continuity equation, the fact that the particles are conserved, we can write down a partial differential equation governing the concentration, which says that the concentration, regarded as a function of position and time, has a time derivative which is given by d times gradient squared of concentration. That's the diffusion equation. We discussed last time how the diffusion equation can be derived or interpreted from a microscopic viewpoint. In fact, we can think of it as an equation which governs the probability distribution for particles in the system. So, to keep things simple, suppose we have a one-dimensional system, and we think of the particles as making a random walk. There's some characteristic time for the direction of motion to be reset. I'll call that epsilon, the time step. Or if you like, the reset time. And we can imagine describing the motion on a lattice with equally spaced sites, with spacing between the sites, which I'll call delta. And in each time step, the particle will take a step either to the neighboring site on the right or the neighboring site on the left, each occurring with a probability equal to 1/2. And then we saw that if we consider a probability distribution which is broad on the scale of the lattice spacing, which changes slowly as a function of position on the scale of the lattice spacing, then in each time step, the probability distribution will be updated slightly. We can describe that as a formal limit in which the lattice spacing delta and the time step epsilon go to 0. And then we obtain a probability distribution for, in this case, I'm in one dimension, so I have a probability distribution for the position in one dimension, which is integer times the lattice spacing delta, and the time in our discretized model is some integer multiple of epsilon. But if we take the formal limit in which the steps are small, we obtain a differential equation, which is just the diffusion equation satisfied by the probability distribution. The time derivative of the probability distribution at a particular site is given by diffusion equation. In this case, we're in just one dimension, so it's the second partial derivative with respect to x of this function of x and t. And we also learned that we can express the diffusion equation in terms of the parameters in our discrete times model, the diffusion equation is the lattice spacing delta squared divided by twice the time factor. So when we take the limit of a very broad distribution, or equivalently a small lattice spacing, we take the limit of G fixed in order to get the situation that's described by the diffusion equation microscopically. And if you like, you can think of this as being 1/2 times a speed of motion. The particle hops left or right by distance delta in the time epsilon, so it moves at a speed delta over epsilon, times a characteristic mean free path. So v is the speed, and you can think of delta as the mean free path. In other words, it's the distance the particle travels before getting its direction of motion randomized. We saw that if you have an initial probability distribution at time 0, which is just a delta function of position, so the particle starts out at the origin with probability 1, then after a time t, the probability distribution will be given by a Gaussian, 1 over the square root of 4 pi dt, the exponential of minus x squared over 4 dt, so the width of that Gaussian depends on the time. And you can think of this as it's really mathematically equivalent to the problem we discussed a long time ago of an unbiased coin flipped many times. The flip of the coin corresponds to whether the particle decides to go left or right, and the position after t steps is the excess of steps to the right over steps to the left. So it's just like our distribution for the spin excess in our simple model of the magnet we discussed in the first week of the class. We look at the root mean squared distance that the particle travels in the time t. It grows like the square root of the time with the diffusion constant soaking up the dimensions, turning the square root of time into a distance. That's characteristic of diffusive motion, that the distance traveled goes like the square root of the time. We can consider the three-dimensional situation, and it's really the same thing. We can imagine the particle now taking a random walk in which its direction of motion gets randomized, and we can describe that on a lattice. So in effect, it's making independent random walks in the x, y, and z directions. On 3 dimensions, you can think of the diffusion constant as essentially the same thing, except, well, I'll use d for the dimensionality. For 3 dimensions, that's 1 over 2 times 2, 1 over 6, squared over epsilon. But the idea is just that if we consider a cubic lattice in 3 dimensions, there are 6 directions in which you can step in each time step. You can either go up or down, left or right, or forward or back. And so the probability distribution will have a vector of 1/6 of it instead of 1/2, because there are 6 ways you can go, which are all equal probable. And our expression, if we start out with probability 1 being at the origin a delta function in 3 dimensions, at time t, we'll have a probability distribution for the 3-dimensional position, which is just the product of this distribution 3 times governing the x, y, and z displacement. So we're interested in the excess of steps up versus steps down, steps left versus steps right, and steps forward versus steps back. So it would be 1 over 4 pi dt to the 3 halves, and then the exponential, well, e to the minus vector x squared, so x squared plus y squared plus z squared divided by 4 dt. And that would solve the 3-dimensional version of the diffusion equation, in which this second derivative becomes the gradient squared for a function of x, y, z, and t. So in 3 dimensions, if I consider the typical distance traveled, now we add up the distance traveled in the x direction, the y direction, and the z direction. That is, we add up the squares. There's a contribution to the mean value of x squared. It's just the mean value of x squared, the mean value of y squared, and the mean value of z squared. So the mean values all grow like 2 dt, and they add up. So if I take the square root, I'll now have the square root of 6 dt. So again, the distance from the origin grows like the square root of the time, and the coefficient of that square root of time is determined by the diffusion constant. So what Einstein realized back in 1905 is that we can use this picture of a random walk to understand Brownian motion. Uncharacteristically, the Brownian motion is aptly named because it was discovered by Brown. And he, in the early 19th century, was looking at a pollen grain suspended in water under an optical microscope. The pollen grain is about a micron in size, and he noticed that it dances around and makes kind of a crazy walk. And if you wait a minute or so, it'll typically move about 6 microns, about 6 times its radius. And I'm not sure whether Brown observed, but others had, or Einstein, that the distance traveled goes like the square root of the time. Brown thought that, maybe the pollen grains are alive and they're swimming. But Einstein had a very different picture, which is that this poor little pollen grain is being pummeled from all sides by random collisions with molecules which make it dance around. Okay? So at any given time, it's being, because of fluctuations, hit a little bit harder from the left than from the right, and from up and from down, and forward and back. And so it executes this random walk in 3 dimensions because of fluctuations. And he gave us, something like this derivation of the diffusion equation from a microscopic point of view. And we also did another important thing, which he explained what the diffusion constant was in terms of other, in principle, measurable quantities, called the Einstein relation. Which is diffusion constant is equal to temperature times something called the mobility. Mobility, or really its reciprocal, is a measure of dissipation, how much friction is encountered by a particle which is moving through the fluid. So if we think of, say, our little pollen grain falling under the force of gravity through the water or whatever it is, there will be resistance to that applied force coming from in this case, the viscosity of the fluid, the fact that the fluid resists flow, and as a result, the particle will reach a terminal velocity, which is proportional to the force. And what that means is that the frictional force impeding the motion of the particle is balancing the force applied to the particle when it reaches the terminal velocity, which is proportional to the force, and the constant of proportionality is B. So the larger B is, the less resistance there is, the less dissipation. Small mobility means high dissipation, low terminal velocity. Okay, so where does this relation come from? I'll describe two ways to derive it or understand it. So the first is, we can imagine a steady state situation where there's a force being applied to the particle, and let's say there are many particles in the fluid, and they're all dancing around because of the fluctuation. And we'll reach a steady state where the diffusive flow, because there's a gradient in density, is exactly opposed by the terminal drift of the particles. So in other words, if we have a gradient, it's more dense here and less dense as you go up. Then because of the high density, diffusion will make the density want to spread upward. And in the steady state, that will be exactly opposed by the drift of the particles, their terminal motion, in which the dissipation matches the applied force. So when the total flux in the steady state is equal to 0, there are two contributions to that flux. There is the diffusive contribution, this law of diffusion, that there's a flux proportional to minus the gradient of concentration. And there's the contribution, which is just concentration times drift velocity, which is what the flux would be if there were no diffusive contribution. So this is, if you like, the drift flux. And this is the diffusive flux. Once we reach an equilibrium situation, they add up to 0. They're equal and opposite. Now, when we're in equilibrium, then the distribution of particles in the fluid should be given by a Boltzmann distribution. If we're in equilibrium with a reservoir at some specified temperature. Concentration proportional to the Boltzmann factor associated with the conservative potential that produces the force. In other words, the force being applied to the particles is minus the gradient of this potential. And in equilibrium, the probability of a particle being at a position should be proportional to the Boltzmann factor with the energy being determined by the potential. So that means if I take the gradient of the concentration, I differentiate this exponential, so I get minus gradient of potential divided by temperature times concentration. And that's just equal to force divided by temperature times concentration. So we know that in equilibrium, since the two contributions to the flux are the same, I have diffusion constant times gradient of potential equals concentration times velocity. But this is just diffusion constant times force divided by temperature times concentration. And this is, since the terminal velocity is just mobility times force, equal to mv times force. So the concentration and the force drop out of the equation. And the conclusion is that diffusion constant divided by temperature is is equal to mobility. That's the Einstein equation. But let's try to understand what's going on from a microscopic point of view. Like I said, these particles are actually, why are they moving around? Diffusively, it's because they're being hit by molecular collisions. There's a force being applied. Think of the particle as moving a little ways freely until the collisions randomize its motion. And during that time, it will accelerate a little bit. The acceleration will just be given by the force divided by the mass. M is the mass of the drifting particle, not of the molecules. And so there's going to be a reset time. Like in the microscopic model we discussed last time, we'll call that epsilon. That's the time that the particle moves before the molecular collision to randomize its velocity and send it off in a new direction. Time for velocity to be reset. To a new direction. Now that acceleration applied for that time is going to allow the particle to attain a component of its velocity in the direction of the force, which is the acceleration times the time, a epsilon. Actually, its average speed during the acceleration will be half that. Because if we imagine it started out with no contribution to its speed coming from the acceleration, starting at zero velocity, winding up at velocity a epsilon, the average speed due to the acceleration, due to the force, is going to be the average equals 1/2 the acceleration times the reset time, or 1/2 f over m times epsilon. And so that means I can think of this as mobility times f, and we can identify the mobility as 1/2 epsilon over m. Now suppose we use the model in which the diffusion constant, in terms of the reset time and the mean-free path, in d dimensions can be the spatial step size, the distance the particle goes before its velocity gets reset, divided by 2d times the reset time. What I said over here. So I'd like to invite you to think of that as 1 over 2d times the square of the speed for the particle times the reset time. So this now, I'll call it capital D squared. It's the speed squared for our diffusing particle. So that means, since this is v squared over 2d epsilon, I can write epsilon in terms of the diffusion constant. Epsilon is equal to 2 big D, the dimension, times big D, the diffusion constant, divided by the speed squared. Okay? So what's the mobility? Again, remember the mobility, we said, would be 1/2 epsilon divided by the mass of the drifting particle. But now let's put in this expression for the reset time epsilon in terms of diffusion constant. So then we have spatial dimension times diffusion constant divided by m of v squared. So now let's make the following leap. Before, when we talked about the equal partition principle, we imagined applying it to the motion of the molecules themselves, and there would be a kinetic energy of 1/2 tau in each quadratic degree of freedom for the molecules in the gas. We can also apply equal partition to the kinetic energy of our drifting particle. Okay? So in thermal equilibrium, I can say that because of equal partition, the kinetic energy, 1/2 mv squared, mean value, for the drifting particle will, if we're in d spatial dimensions, there will be a 1/2 tau because of equal partition for each one of the components of its velocity in d dimensions. Okay? So in other words, for mv squared, I can take d tau by equal partition in classical statistical mechanics, and substituting that into our expression for the mobility, we get the Einstein relation again, diffusion constant divided by tau. This argument is a little more crude than the one I gave initially, which is a bit more respectable. We happen to get exactly the same answer. If we'd gotten the same answer up to some constant like 2 or pi, I wouldn't have been too disturbed about it. But we can see that why it makes sense for the mobility to go like diffusion constant divided by tau from the point of view of the microscopic model if we think of the diffusing particle as having a kinetic energy set by equal partition. Yeah.
How did he drop the brackets?
Yeah, well, so I'm saying that we're watching the particle over some long time compared to, the typical fluctuations in the speed. And so if I want the mobility, the particle actually is, its speed is fluctuating, but we're interested in its average strip speed with those fluctuations averaged out. And so I'm just going to take the average kinetic energy of the diffusing particle in this estimate. Okay. So that's the Einstein relation again. So the way Einstein used this was kind of interesting. He used it to estimate Avogadro's number, which was a big deal at the time because there were various people using various points of view trying to estimate Avogadro's number and get a better understanding of whether they should believe in the reality of atoms. So as we've seen, what the diffusion equation tells us is that if I look at the mean square distance traveled by a particle, let's say now in 3 dimensions, that if I divide that by the time, I get 6 times the diffusion constant. And the Einstein relation tells us how to express the diffusion constant in terms of the temperature and the mobility. And uncharacteristically, I'll write in Boltzmann's constant for a reason we'll see in a minute. For tau, it's actually kT times mobility. But Einstein knew what the mobility is of a sphere suspended in water because there was a formula that Stokes had derived, which I won't really explain because it requires explaining what viscosity is, which is a whole lecture in itself. But according to Stokes, if I consider a sphere moving through a fluid which has some viscosity or resistance to flow, eta, then the mobility can be written as 1 over 6 pi viscosity times r, which is the radius of the sphere. Okay. So bigger sphere means it's harder to push the ball through the fluid because of the viscosity, and therefore smaller mobility. And from looking in the microscope, Brown knew, or others knew by that time, about how big the pollen grain is, that it's about a micron in size. And the viscosity of water was also known from other measurements. So the mobility was known. What was not known so well at the time was Boltzmann's constant. So Einstein used this to derive a value of Boltzmann's constant. And you can translate that into a statement about Avogadro's number, because the Avogadro number is ideal gas constant R divided by Kb. That is the Boltzmann constant. If you write pressure times volume not as n tau like we usually do, but as n RT, where now n is the number of particles in moles. I don't know what stands for n. Well, the constant r was known, and r is just n, the number of particles in a mole times Boltzmann's constant. So it determined Boltzmann's constant and hence Avogadro's number. Yeah.
How did he manage to get the value of capital D?
Capital D?
Yeah.
Yeah, he got it from the Einstein relation. He knew that it was the temperature in units of energy, which is Boltzmann's constant times the temperature in degrees Kelvin.
But he didn't know Boltzmann's constant.
Yeah, that's right. He used this to find Boltzmann. Oh, how did he? Okay, right. He used it. He did this. He said, okay, here's a particle, and it has a size of about r equals 1 micron, or micrometer, and look at it under a microscope. It's big enough so you can see it with a good optical microscope, and it jiggles around. And then you can, with a stopwatch, verify that the distance it typically travels scales like the square root of the time, or distance squared scales like t, and with a constant of proportionality, which you can then determine by looking at how far it goes. And that's how 6D can be extracted from the data. If you put in the viscosity of water and R equals a micron, then the typical distance traveled is about 6 microns in a minute. So you don't have to, you look at the particle moving around for a few minutes, and you do it many times, and you can get a pretty good estimate of this expected value of x squared. And that means you know D from observing the diffusing particle. And then Einstein had derived that D is kT times B. B was known, and so Kb was determined. Hence Avogadro's number was determined, and he got 6 times 10 to the 23. But in this case, it seemed like that determination of Avogadro's number was especially compelling evidence for the reality of atoms, because Einstein understood, I don't know, should I do it again, that the interpretation was that the pollen grain was getting hit from all sides, and the craft was out of it by all these molecular collisions, and that's why it was drifting around. It was a controversial subject in the early 20th century, whether atoms were real. The philosophically minded questioned it, like Mach, because he said, well, you can never see them. It's just a theory. Well, now we have lots of ways of seeing them. But this was the first hint that you really could see them, because the jiggling around of the pollen grain was evidence of the pollen grain being subject to molecular fluctuations. Okay. So this Einstein relation was one of the first examples of something that's called a fluctuation-dissipation relation. Diffusion constant equals mobility times temperature. An indication that there's some connection between these two things. Mobility has to do with dissipation, the resistance to flow for the particle going through the fluid. Actually, they're reciprocal of the mobility is a measure of dissipation. High mobility means low dissipation. So this is a measure of dissipation. And we see from the interpretation of diffusion in terms of a random walk, or because of this behavior, which you can observe when a particle is suspended in a diffusive medium, that the diffusion constant is a kind of measure of fluctuations. How much the particle is walking around is random, that's what I mean by fluctuation. And there's a relationship between the two things, and it involves the temperature. So if you fix the dissipation, in this case the mobility, then as you crank up the temperature, the fluctuations get stronger and stronger, arising because of the molecular collision, pummeling the poor pollen grain harder and harder. We talked about another fluctuation-dissipation relation. Does anybody remember that? It was a while ago. Maybe this will remind you. So we can think of it this way, that there's some power being dissipated by the motion of the particle. Oh, that gave it away.
Johnson noise.
Johnson noise, right. In other words, the power or the particle that's shaking around is like a force times the speed, and if you think of the speed as being the terminal velocity, v squared divided by the mobility, according to definition of mobility. And so if I look at the mean square distance traveled by a diffusing particle and divide by t squared. So this is like v squared over b. So it's something like the power being dissipated by the diffusing particle subject to force. And it's, well, in d spatial dimensions, it would actually be equal to 2d times the temperature times 1 over t. So you can think of t as a characteristic time over which you're watching the motion of the particle, and the 1 over t is kind of like a frequency thing. So this is analogous to the case of Johnson noise, which according to Nyquist's formula, the power is I squared R, and that's 4 times the temperature times the frequency band in which we're watching the fluctuations of the current or the voltage. Okay, so if you like some characteristic time of observation for the fluctuating current. So in both cases, the temperature controls the scale of the fluctuations. There's something that measures dissipation. Here it's R, the resistance in the circuit. Here it's 1 over B. 1 over B is a measure of the dissipation for the particle moving through the fluid. And the size of the fluctuations scales with the temperature. Okay? Higher temperature, larger fluctuations. That's a fluctuation-dissipation relation. So tau controls size of fluctuation. So there's one other topic I guess I'd like to talk about for 40 minutes or so. Before I do that, let me remind you, in case I forget to do so at the end of the class, that there's a final exam. I expect to post it today. It'll be due at the end of the exam period, which is 5 p.m. Friday, tomorrow. The format is similar to the midterm. The rules are the same. It'll be 4 hours this time. You can take a 15-minute break that doesn't count sometime during the 4 hours. There will be 4 questions. So it's a lot like Passover. 4 questions, 4 hours. And what are the questions about? You know, both content of the courses, fair game. But the course is kind of cumulative, so chances are, if I were writing this exam, I did, that I would draw more heavily from some of the latter topics. What were those? It seems to me that we talked about phase transitions quite a bit. And wasn't there something about heat engines? And things like the Bose-Einstein and fairly direct distributions and quantum gases and things like that. And everything else.
What about kinetic theory?
Sorry?
What about kinetic theory?
Oh yeah, good point. That's exactly right. And kinetic theory. I'm glad you reminded me. I forgot Einstein. And oh yeah, and I'd appreciate it if you're willing to, if you'll fill out the T2FR questionnaire. It helps me. And I guess you get an email telling you how to do that. I got some feedback from that survey that you did earlier, and there are 2 main things I learned. Actually, I want to see if among you, my biggest fans who are actually here, if there's a consensus about these things. One is the homework. Some people don't like the problems in K and K very much. They like it better when I write the problems. So if you suppose, other things being equal, you could do a KK problem or a JP problem. How many like KK problems better? They kind of tell you formula sometimes. How many like the problems I write better? Okay, so that's consistent with the results of the survey. Biggest complaint about the lectures, surprises me, my monotone voice. I need to modulate my voice more. How many would like me to modulate my voice more? More? Less? Modulate my voice more. Okay. Modulate my voice less. That's not the way I'm doing it. Okay, so it's somewhere in between here. I don't know. All right. So I'll practice the modulation and the rest of the lecture. And what I want to talk about is Maxwell's demon.
So for final we have 4 hours and 50 minutes total, right?
Right. You're supposed to, it means 4 hours when you're actually sitting working, writing, and 15 minutes where you go to the bathroom or have a snack or something like that. 4 hours and 15 minutes from start to finish. Okay? Okay. So, let's talk about Maxwell's demon and the second law. So, of course, the foundations of thermodynamics, the fun of this course has been to see how we can recover thermodynamics from a microscopic point of view. And really, the germ of that idea arose in the 19th century, particularly because of the work of Boltzmann and Maxwell, names we've heard a lot. But Maxwell had some qualms about the microscopic view of the second law of thermodynamics, which he expressed in an article in 1871, which he called Limitations of the Second Law. Maybe it doesn't always work, he said. He imagined the following situation. Suppose I have gas in a box. One of our favorite things to consider. And suppose the box is divided into two parts. There's a partition in the middle. I'll call the part to the left of the partition A and the part to the right of the partition B. And there's a little door I can open and shut. When a molecule is heading towards the door, I can open the door and let it pass, or I can close the door and it bounces off the door and doesn't pass. So, since you probably don't believe that I can do that, Maxwell said imagine a demon with great observational power who can watch every single one of the molecules in the gas. At all times, he's watching where they go. And for the purpose of this discussion, we can think of the dynamics as being completely classical. Okay? So you really can know exactly what, in principle, you can know exactly what the position and the speed, the velocity is of every molecule, and that's what the demon knows. And he allows any molecules that are going faster than me. There's a Maxwell distribution of velocities, right? Some are going faster, some are going slower in equilibrium. And so when he sees fast molecules heading towards the door, he allows them to pass if they're going from A to B. But if they're trying to go from B to A, he doesn't let the fast molecules through. He does let slow molecules through, though. So the molecules that have a kinetic energy less than the typical kinetic energy are allowed to pass from B to A. The ones with kinetic energy greater than typical kinetic energy pass from A to B. And the demon keeps doing this for a long time. And what happens? Well, A is going to cool down, and B is going to heat up. So we started out with all the gas and the molecule at the same temperature, governed by a single Maxwell distribution, but after a while, A is cooler, B is warmer. But as far as one can discern, there's no reason in principle why the demon couldn't do this expending a negligible amount of work. He's only got to move this little tiny hatch open and shut to let one molecule through. It doesn't sound very hard. Okay? And he's a very powerful demon, an excellent engineer. He manages to make a very efficient little door. He lets them all go through. He's watching them all the time, and that requires a very vigilant demon who doesn't necessarily watch things. Look, I'm watching you. Am I working? No. So it's not clear that he has to expend more than a negligible amount of work. So the work is negligible, or it could be. Yet, one side cools off, the other heats up. That violates the second law. If there's no dissipation, because the entropy of the universe is going down. And in fact, if I'm eager to, lower my dependence on imported oil, I could do this for a while, and I'm running a refrigerator, and then I could let the heat flow from the warmer side to the cooler side and operate a heat engine, from my laptop. Okay, so that doesn't. Something seems wrong here, and Maxwell knew there was something fishy about this, but he couldn't quite put his finger on what was wrong with it. So it seems like, under these circumstances at least, second law of thermodynamics can be violated. Granted, it requires a fairly advanced civilization maybe to carry out this program. But some centuries from now, maybe we'll be able to do it. And therefore, everything I told you through the year is, it's all garbage. Second law is wrong. Yes.
Wait, what's your argument for the work is negligible here?
Well, I guess that's what we want to examine more closely. Right? We'd like to understand what are the real limitations on carrying out this procedure.
No, but what was your official argument for the work is negligible?
Why did I say the work was negligible? Because, first of all, observing the position and momentum of all the molecules, it's not clear. Something we should think about, right? Whether that requires significant expenditure of energy, just watching, okay? And secondly, I have to operate the little door.
How do you make this slower? How do you make only the slower?
You just wait until one's coming.
Oh, yeah, right. So they're bouncing around, right? So every once in a while, if I keep the door closed, they're going to bounce where the door is. Okay, and instead of letting them bounce, well, I either let them bounce if, from coming from one side they're too hot, or coming from the other side they're cold. Otherwise, I let them through. Okay.
And you say the move of the door is
So that's going to cause some flow of heat from one side to the other, right? One side will get hotter, the other side will get colder. Second law says you shouldn't be able to do that without expending some work. The question is, why is there some unavoidable expenditure of work in this process, if indeed there is? That was the question that Maxwell raised but did not resolve. And some years later, quite a few years later actually, Szilard took up the question. This was just a few years before he became apparently the first person to conceive of a nuclear chain reaction. And he thought about Maxwell's proposal, and he made a number of important conceptual contributions in this paper. For one thing, he for the first time suggested a kind of connection between entropy in thermodynamics and information, because he seemed to feel that it was very important in doing our entropy accounting to think about the demon himself and how his thermodynamic state might be changing because the demon is acquiring information when it observes the state of the molecular gas. That was an idea which, 20 years later, was taken much further by Shannon, who founded modern information theory in 1948. He also, apparently, was the first person to think of the concept of a bit, that we can express information in terms of two-level systems. He didn't call them bits, but he had the idea. And the idea that we could quantify information by how many bits we need to record the information, how many letters which we take from values. And so Szilard said, well, it's helpful to think about Maxwell's idea in concrete terms. Let's make it as simple as possible. Always a good thing to do when you're a physicist. Kind of come and boil down the idea to its simplest realization, which you have the best chance of understanding. So he focused on the question, what is it that really is irreversible that's going on here? He noted that the demon is going to have to measure. He wondered, is there some dissipation associated with the demon acquiring information? He noted that the demon was going to have to store information in a memory, and he wondered about whether that involved some kind of irreversibility. And he was a little bit cagier when it came to this last one, but he also seemed to realize that the demon will need to reset himself, which means that information will have to be erased. And he tried to put his finger on what the catch was, why, in fact, the total entropy of the universe maybe isn't going down if we analyze this process carefully enough. And here's a version of the demon machine that he envisioned. Said it's gas in a box. What's the simplest gas? What's the simplest gas?
Monotonic, ideal gas.
Yes, but even simpler would be just one molecule. Okay. 0 molecules wouldn't do, but one molecule, we can talk about a gas. Now, of course, if we want to do statistical mechanics, we want to have many molecules, but Szilard said, well, okay, we can consider many one-molecule gases and apply statistical mechanics to that ensemble. Well, let's just look at one molecule at a time. So there's a box, and there's a molecule in it, and it's bouncing around. It's in contact with a reservoir. The reservoir is at temperature tau. So we're going to consider isothermal processes at temperature tau, and here's how we'll try to get some useful work without, useful work for free, essentially, which would lower the entropy of the universe. So there will be 4 steps. The first step is we will start out with a box which has no partition. There's a molecule in there somewhere. And then we will suddenly close the door, partitioning the box into 2 parts, the left part and the right part. And when we do so, we will capture the molecule in either the right side or the left side, the 2 occurring essentially equal probably. But we'll catch it on one side or the other. Okay? That's the first step. We partition into 2 parts. But we haven't at this stage observed whether we caught the particle on the right side or the second side. So the second step is to measure. So the demon learns whether the molecule got caught on the left or the right. Which of the 2 possibilities is it? Is it stuck on the right side or on the left side? So now we know. Let's say we found out that it's on the right side. So then what I'll do is I will allow the partition to move. I've got a molecule that's on the right side. It's bouncing around off the walls. And I'll load this now movable partition with the weight. There's a little rope going around the pulley. Weight. Actually, yeah, I guess that's right. So I load the thing, and now I quasi-statically allow the gas to expand. It's going to be bouncing around. It's going to kick the movable wall every once in a while, and it's going to slowly move the wall to the left, flipping away. Okay? So the third step will be isothermal expansion. Of gas with a loaded movable wall. So gradually the wall moves until the wall has moved all the way to the left side. Okay? And now we have no wall, and we have a single molecule bouncing around inside the unpartitioned box. Yes?
How do we know it will expand all the way that way? How do we know it won't just come to equilibrium, like...
There's no particle in the other.
Well, it's an isothermal process,
Oh.
so it won't actually lose energy. It'll stay in contact with the reservoir at temperature T, so it'll keep bumping into the wall and pushing it each way. Okay?
So you took the energy to raise the weight out of the reservoir?
Sorry?
So you took the energy to lift the weight out of the reservoir?
The weight itself, it doesn't really have to be in contact with the reservoir, but the energy to lift the weight is coming from the reservoir, so that the molecule is doing work of lifting the weight. Where's the energy coming from? It's coming from the reservoir, because the molecule will stay in thermal equilibrium with the reservoir at temperature tau. But in order to stay isothermal while it keeps pushing the weight, it has to acquire energy from the reservoir. So the total amount of work that's going to be done I'm going to put the K's in for the time being. Boltzmann's constant times temperature times log 2. This is actually a reversible isothermal process of the sort that we talked about before. It just happens to be just one molecule. So before we said that when the expansion occurs at constant temperature, that the entropy increases by, so this is now the conventional entropy, so I should put in a factor of K, Boltzmann's constant, times the log of the final volume after expansion divided by the initial volume before expansion. I guess I didn't explicitly say so, but I was imagining that I put the partition right in the middle, so when the wall gets pushed all the way to the left side, the volume has doubled. So the entropy, in this case, when n is equal to 1, and the ratio of the final volume to the initial volume is 2, the entropy increase is just k log 2, and the amount of work done isothermally then is kt log 2. The work, according to the first law, is just the temperature times the change in entropy. So there's heat flowing from the reservoir into our one molecule gas, and that heat is doing the work. Okay, we lifted the weight, but there was no waste heat. Okay, we did this at temperature tau. We had reservoir temperature tau. We had no zero temperature reservoir. We didn't have to produce any waste heat. So no waste heat. We only had one temperature, so one reservoir, temperature tau. We were able to steal kt log 2 of energy from the reservoir and do useful work with it. We did work, and the entropy of the whole world don't forget about the entropy of the whole world. The number of states of the gas expanded by a factor of 2, so the entropy of the gas increased. And that increase in entropy we were able to use to do useful work without any waste heat, and that violates the second law. Right? This is better than Carnot efficiency. We had no cold reservoir, but we could do work. We just drew it right out of the reservoir at temperature tau. And then the fourth step is we start the whole thing over again and do it again. So we can keep doing it over and over again. Each time we get work out, kt log 2. About half the time, the molecule, when we measure it in step 2, is going to be on the left, half the time on the right. We use that information to know which way to load the movable wall. Okay, so the weight will always be lifted. But every time we do kt log 2 until I'm tired of using my laptop. Well, the reason I emphasize that we can repeat this is because, like in our analysis of a heat engine, we wanted to consider a cycle that we could repeat over and over and over again. So we wanted to come back to the initial situation, so everything would be the same again, and then run the cycle again. It seems like I can do that here, right? I started out with a molecule in the unpartitioned box, partitioned it, I let the gas expand, and then I'm back to a molecule in an unpartitioned box, so I can do the thing over again. Well, what we should always ask when confronted with a heat engine or refrigerator that seems to do paradoxical things is this cycle really closed? Is everything the same at the end of the cycle as when we began, or has something changed that we need to keep track of when we run the cycle over and over again? Okay. Well, let's think about the demon himself or herself. Is the demon in a different situation, a different state at the end of the cycle than at the beginning?
Yes.
How so?
At the beginning, he doesn't. Well, at the beginning, there's uncertainty in which half the molecule is, but at the end, there's 100% certainty that it is.
Yes, he has recorded some information. The demon, no, because the demon has stored information. In his memory. He had to store it, right? He made the measurement to figure out whether the molecule was on the left or the right. He wrote that down. Then he was able to figure out how to load the wall during the isothermal expansion. What he stored was 1 bit. Whether it was left or right when he measured it. Okay. So really, the system that we're considering is not just the gas, the one molecule in the box. It is the one molecule in the box and the demon's memory. Okay. We brought the gas back to its original state, but not the memory. Now, the demon might have a lot of memory, and if he has a finite amount of memory, eventually he's going to use it up, and he won't be able to do this anymore. He won't be able to store another bit unless he what? Right. So the demon memory is limited. He must eventually erase. If he wants to reuse them. If he doesn't, if he just stops after he runs out of memory, well, then we have to remember that the memory itself is, well, we have to ask how we should model that. If it's really a perfect memory, it doesn't have any fluctuations, it is a zero temperature reservoir. It's a system at zero temperature. So we shouldn't be so shocked that the demon was able to get some useful work out because he had a low temperature reservoir. That was his memory itself. Okay. But if we want him to keep doing this over and over again, and he has only a finite amount of memory, eventually he's going to have to erase. And so we have to ask the question, what is the thermodynamic cost of erasure? This was a question that was actually asked by Rolf Landauer in the early 60s, and his answer was that erasing a bit requires work. An amount of work which is at least kt log 2. Log 2 because we're erasing one bit. Okay. So if Landauer is right about that, then there's really no paradox. If we want to really have a closed cycle, and we want to put the demon's memory as well as the box back where it started, then we're going to have to pay back the k log 2 of entropy that we withdrew from the reservoir during the erasure. The erasure itself will be a dissipative process. It will dissipate heat. Entropy will go back to the reservoir. Everything is back where it started, but we got no useful work out net because the work that we did using the one molecule gas, we had to pay back when we erased the demon's memory. Okay, so the question is why? So this is called Landauer's principle. Stated in 1961.
So this guy didn't resolve the problem?
Well, he didn't specifically discuss Maxwell's demon. Landauer's main point was quite interesting. And I'll come back to that at the end if we have time, which maybe we won't, so maybe I should say it now. He worked for IBM, okay? And his job was to think about computing. And he said that there's a thermodynamic cost to computing which is unavoidable. Because when you compute, you necessarily erase information. Because logic gates are not logically reversible in general. They can destroy information. He said that it would cost about kT in energy each time you do a gate in a computer. And so you'd never be able to reduce the energy cost of computing down to zero. And that was his main point. He was wrong about that. But he did state correctly that whatever is logically irreversible has some non-zero thermodynamic costs, in particular erasure. Erasure is something that once it's done you cannot undo. That's the sense in which it's logically reversible. His statement was that if it's logically reversible, that means it's thermodynamically reversible. But it wasn't until another 20 years later that Charlie Bennett really completely explained what was going on, namely that Landauer's principle is the key to understanding why Maxwell's demon doesn't violate the second law. I'll write that down. Bennett, 1982, Landauer's operation principle means Maxwell demon does not violate the second law after all. You don't get something for nothing. So to try to explain why erasure is thermodynamically irreversible, why we need work to do it in particular, the simplest thing to do is just to consider some model of a memory and ask what we need to do to erase it. So as long as we've invested the effort to describe Szilard's machine, I'll imagine that the demon uses a similar machine for his memory. Okay? It's a Szilard box. But the argument would apply to any model. When the demon wants to record a bit, he puts a molecule in a box. The box is divided into two parts. He either puts a molecule on the left side, let's say the right side, and he calls that storing a 0, or he puts the molecule on the left side, and he calls that 1. And if he's doing this Szilard cycle many times, each time he stores another molecule in the box to keep track of the information, which he's got to have on hand when he loads the partition. Was it on the left side or the right side? Okay. So I'm using the box two ways. I'm using it as the object that is running a heat engine cycle, but I'm also using it as a memory, another box, which I can use to record information. And now, after I've done this many times, I've got lots of molecules in boxes, each one stored on the left or the right. Okay? Therefore, the cycle isn't closed. Every time I ran the cycle, I stored another bit. Eventually, I want to erase all the bits. How do you erase a bit? Well, in this case, I have to do something, some physical process, which, irrespective of whether the initial recorded value was 0 or 1, will take the bit to the same final value. Give me a 0, irrespective of whether I had a 0 or a 1 to begin with. So that's what erasure is. It's a map from a bit to a bit. And no matter whether the bit is originally 0 or 1, it maps it to the same value. Let's call that 0. Okay. So when I say it's irreversible, I mean this is not an invertible map. If you know the output of the erasure, namely 0, you don't know whether it was initially a 0 or a 1. They both got mapped to the same value. So non-invertible map, I call that logically irreversible. You can't undo it. So how would I erase that information? I've got to do something like this. No matter whether the molecule was on the right or the left initially, I have to make sure it's on the right finally. Okay. Well, here's a way you can do the erasure, and the analysis would apply no matter how you do it. Here's an erasure procedure. Erasure means that I have a way of storing a 0 or a 1, and no matter how it was stored to begin with, I want to have a 0 at the end. Okay. And I have to apply a procedure which works the same way, no matter whether it was a 0 or a 1 to begin with, because it would work differently depending on whether it was a 0 or a 1 to begin with. I would have to record that information.
Can't you just remove the partition?
Well, I could remove the partition, but then that will not take the memory back to its original configuration. I won't know whether it's a 0 or a 1. If I say that the 0 state is the state where it's on the right side, and the 1 is the state where it's on the left side, if I just remove partition, now it's neither on the left or the right, it's bouncing around. Okay. So I can try to force it to be on the left or the right. And in fact, I can't just put the partition back because that would just, I wind up with a random bit. It might be over here or it might be over here. Okay? So I want to do something which will make sure that it's always on the right no matter what. So what should I do? I should do is compress the gas. Right? So I start out with a movable wall way over here on the left. The molecule is somewhere in the box. I'm in contact with a reservoir, temperature top, and I compress. And I see statically, little by little, partly compressed here. When I'm done compressing, the wall is in the middle again, and it's guaranteed that the molecule is on the right side. Okay. When I did the compression, I had to do work. I was actually reducing the entropy of the molecule, reducing the volume that it occupies from the final volume 2 to the initial volume 1. So the amount of entropy or entropy of gas are reduced under isothermal compression by k log 2, because the final volume is half of the initial volume. So where does that entropy go? Well, where does it go? It goes back to the reservoir, right? So there's going to be, because I'm compressing, I'm doing work on the gas, but it stays at temperature top. So there's going to be heat flow from the gas back to the reservoir. So W equals K T log 2 is work done, hence heat flow back to reservoir. So the entropy of reservoir increases by K log 2. So when I got work from the reservoir operating Szilard's machine, I pulled entropy K log 2 from the reservoir. I used that heat to do work KT log 2. Energy KT log 2 that I drew from the reservoir. But it wasn't a closed cycle, because I wound up with a bit stored in the daemon's memory. To get a really closed cycle, I've got to erase that bit. The erasure of the bit, though, is a dissipative process. It sends, when it's done as reversibly as possible, entropy K log 2 back to the reservoir, and it requires that we do work KT log 2. The general principle is that erasure is a procedure that compresses the phase space, reduces the number of possible states of the system. Right? That's what we mean by erasure. If we have a bit, it means there are two possible states. The molecule could be here or here. When we erase, no matter what, we want it to be here. And here there were two states. Here there's only one. We've lost one bit of information, and so we've reduced the entropy by K log 2, and there's no way we can get around it. So that's the resolution. We have to, it's a little bit surprising when you first hear it, because you think that remembering things is hard, when you're studying for an exam, and forgetting things is easy, but it's actually the other way around. It doesn't cost any energy to remember something, but it costs KT log 2 to forget a bit. Okay? So if you work really hard, you can forget everything I told you. Chances are, in 10 years or so, you will have successfully done so. But I hope. Okay, thank you.